So in this video, we shall address experimental designs, and we are going to talk about three of them today. There is actually more, but for the sake of this course and also the most popular, simplest ones are the ones I'm going to do today. But first, just keep in mind that whenever you run an experiment, if you want it to be a good one, it needs to go through some sort of a filter. And that filter is what we call the principles, good principles of experiments. And they are comparison, blocking, randomization, and replication. So these are the four principles that you want to make sure you go through. Whenever I don't care what design you work with, keep those four pieces in mind to make sure that your experiment is a good one. So I'm going to begin with the first one, which is probably the simplest. It's called completely randomized design. So let's say you have a private boarding school, and they want to know the best place to study for students. And let's say they are only exploring three areas: students studying in their room, students studying in the library, or study hall, like students studying in the presence of a faculty member. And so obviously, the experimental units are going to be students in this case. Experimental units don't have to be people. They could be cars. They could be paints. It could be mice. It could be anything, right? Anything. It could be a cells, like a seller, like a wholesaler, so to speak, right? Let's say you get something from 5 wholesalers. It could be anything. Whenever the experimental units are people, you have the right to call them subjects. So if you don't see subjects, that means experimental units could be anything, okay? If you want to be safe, just call them experimental units because that is more encompassing than the word subjects. So let's say, here is how I would address or how I would tackle completely randomized design. I would begin with my treatments. Treatments doesn't mean you're taking a pill. So basically, you're gonna impose a treatment on the units, on the subjects, right? And that's why it is called an experiment in this case. Because you are only exploring 3 areas on campus, you have to have 3 groups. So I work backwards. And let's say we are dealing with a multiple of 3 units. Let's say you have 1,000 students and you want to select a sample, a good sample of 90 students. So clearly you want to use an SRS to make sure, or stratified random sample. Make sure that's the 90 people you want to pick. Let's say we want to pick an N to be 90, okay? This is my sample. Make sure this 90 reflects the population of interest, which means all students, which means 1,000 students, okay? So make sure you do some sort of a simple random sample or a stratified random sample or something of that sort to make sure that the 90 that you picked reflects the population of interest called the student's body of 1,000 students. That's the first thing you need to do. And then, of course, you want to split them into 3 groups because I have 3 treatments. So maybe we'll put 30 in each group, right? It's also important that these 90 are not split randomly, like the first 30 that show up to the door, you send them to group 1, okay? They have, every member in this group should be completely due to chance. And that's why we use the word completely randomized design. In other words, a person in this group has an equal chance of being in this group or that group. So you may want to find a way to split this in such a way that each member in each group has an equal chance of being in a different group. You can't just have the first 30 people that show up. Let's say you want to interview 90 students, okay? That's the number you focused on. And the first 30 that showed up, you put them in group 1. That's not fair. right? Because maybe those 30 students tend to be more responsible, and they show up on time, they show up early, right? So you want to randomize these 90 people into groups of 30 each. And then for each group of 30, you give them this treatment. So maybe this group study in a room for maybe 50 days or 20 days. Again, replication is important. You don't want to do it for one night only. You want to do it for many days. Group 2 goes to the library for those many days, and group 3 goes to study hall for those many days, and then you compare the results. That is called a completely randomized design. So let's go to the second one. The second one is more encompassing of the first one. So the second one, I'm going to use the same example. I have, let's say, 90 students that I'm choosing, but let's say the school believes that older students tend to behave differently from younger students in terms of where they study and how efficient they are where they study. So you may want to stratify your 90 students or 100 or whatever the number you picked into the older ones, maybe the seniors and the postgraduates, and the uppers, maybe we call them the juniors, right? And then the younger ones, the freshmen and the sophomores, 9th and 10th grade, or something of that sort. So you want to stratify them, which means you want to put them into blocks first, 2 blocks. Does it have to be 2 blocks? No. You could have 3 blocks, right? And hence the word randomized block design. So as soon as you split them into 2 blocks, then you go through the entire process you just went through with completely randomized design. So this is exactly what I just did before. And this is exactly what I just did before, right? So this is a completely randomized design, and this is a completely randomized design. To call it a randomized block design, first you split them into blocks, and then you go with the completely randomized design. So I don't need to repeat myself because I went through this entire process. Now, of course, you compare the students who studied in these particular areas, and you do the same thing for the other groups. I call them group 1 prime, group 2 prime, group 3 prime, okay? Now, what is important also is not to compare these two. In fact, if you were have to compare these two, you shouldn't have split them in the first place. So you just compare older students in terms of the treatment that they received, and you compare the younger students in terms of the treatments that they have received. It's very simple. So think about this as a special case of this, right? This is a completely randomized design, and this is also a completely randomized design, okay? Think of this as a square, and think of this as a rectangle, so to speak. All right, the last one is called matched pairs design. What is unique about this matched pair design is you can't have more than 2 treatments. Now, I had 3 treatments, right? In all of these examples, I could have had 2 or 4 or 20, right? But even if you just have 2, you can't call it a matched pair because there are 2 conditions. One is you have to have 2 treatments, and number 2, the same subjects, I'll address this later, the same subjects or experimental units receive both treatments. In here, group 1 did not receive all the 3 treatments or 2 of them. Each group received 1 treatment. In here, it's different. The same experimental units receive both treatments. So here is an example. Let's say you want to know which type of gas is better for cars. Is it this grade or that grade? Or is it this type of gasoline or that type of gasoline? So my experimental unit in this case will be just one car, let's say. Okay? That experimental unit, there is one of them, will receive both treatments. These are the treatments. Type 1 of gasoline and type 2 of gasoline. Now, how do you do it? Of course, you fill the car with this type of gas and you run on it until the tank is empty, completely empty, and then you fill the same car with the second type of gas, and then you compare the results. And you say, oh yeah, I got more mileage by using this type versus that type. Or maybe when I went for a tune-up, my car did better when I used this type of gas. Let's say you use this one for many days, and then you empty the tank, and then you did this for many days, you know, and then you compare the hood. You go under the hood. A mechanic would look and say, "Wow, this had an effect on the car in a bad way or a good way." The point is, you can compare after you go through these two treatments, the same experimental units. Now, that doesn't mean it is always one experimental unit. You could have many done separately. That's why I put 3 dots here, because of replication. You don't want to just do it to one car and pass the judgments on the type of gas. Maybe you'll pick 20 cars, but each car, see in here we picked 90, right? In here we picked 90 students. In here we pick one car. But how many of them you do? You could do it as many times as you want, but there is only one car. All right, so you could do it with car number 2 and compare, car number 3 and compare, and then make a decision. Hopefully you'll do it for many cars, but each experimental unit take both treatments. Very important. Okay, now I said 2 treatments, yes, and 1 experimental unit, one car, one car, one car, one car. But I said or similar. It is possible to have, let's say, 2 experimental units. You might say, well, that sounds like a contradiction. You just told me there should be only 1. Well, sometimes we can't do it with 1. So I'll give you an example. Let's say instead of dealing with cars and type of gasoline, I'm dealing with students, and that student is taking 2 types of tests, a verbal test and a written test. Let's say it is the same one. In here you write it, but in here you take an oral exam, but it's the same test. Well, you couldn't take student A. Let's go back here. You couldn't take student A and take the oral exam as a treatment, and then you take the written exam after you finish the oral exam, because you would have seen the exam. Does that make sense? When you empty the car and then you fill the car with a different type of gas, those are mutually exclusive. Like, they don't talk to one another. They're disjoints. But if I have a written exam and an oral exam done with the same students, we've got a problem, because you will definitely do better the second time around because you have seen the test. So in that case, what we would do is maybe pair them up in such a way that you pick students of similar ability. And that's a decision the researcher has to make. You know, will you look at their GPAs? Will you look at the last 3 tests they took and whether or not those 2 students are similar? So they resemble like one student, so to speak, but then you're not going to take both exams because you would have seen the first one when you take the second one. That is the only reason why we pick similar experimental units, because if you just take one, it kind of defeats the purpose. So you run through this again, but with 2 students. So student A will take just the verbal, not both, and student B will take just the written exam, and then you compare the results. How many times you do it? I hope you do it many times, right? You do it with students A and B, that's 1, and then you do it with 2 more students of similar ability. Maybe they both have around 80% on their last 5 tests. Maybe based on some placement exam, these 2 students sound or seem to be similar in their ability. Maybe you look at their GPA. I don't know what you would do as the consultant or the researcher, but the point is those 2 students should have similar ability, and you give a test to each one of them, and then you compare. That is very similar to this, except that you don't take both treatments. Student A only takes one treatment, and student B only takes one treatment, because you can take both tests. Okay, makes sense. So that should be it. I hope as you finish this video, go back here and see if you could fulfill all the principles of a good experiment. You could do it here as well, right? Make sure you can run an experiment that fulfills the randomization, the comparison, the blocking, and the replication. And you should do it for this one as well. And that's why I chose this experiment many times. Maybe you'll do it with 20 types of cars, right? Or the same type, let's say a Honda, but you do it with 20 separate cars called Honda, right? So that's how you go about designing an experiment. I hope this is helpful. Take care.